All right, let's look at the wave and sound problem types here. So the first one we have is it's a wave problem because we have energy being transferred from one point to another point. And so we can use speed of the wave, the speed of the energy that is equal to the frequency times the wavelength. And the frequency is equal to 1 over the period for these waves. I have here a transverse wave. The wavelength is from one point to another point of the same type, so crest to crest or trough to trough, something like that. And then the amplitude is from this equilibrium position, this undisturbed position of that medium. There is also the longitudinal waves that move back and forth, and so they create a pressure curve that looks like this. All right, next we're going to look at intensity and sound intensity level. This is if we're dealing with the intensity of sound waves. So the intensity of a sound wave is equal to the power divided by the area over which that power is spread. And so it's 4 pi r squared would be the surface area of a sphere. So if you create a sound, that sound travels out equally in all directions, covering an area of 4 pi r squared, r being the distance away from that source. Beta, this is the sound intensity level. So this is what we use to talk about intensity, but maybe in a scaled version that's a little easier to understand. So the sound intensity level is equal to 10 times the log of the intensity divided by the threshold intensity, the minimum intensity you can hear, which is 1 times 10 to the negative 12th watts per square meter. Next, we're going to look at harmonics of strings. So this is when you have a string fixed at both ends and it's vibrating. The frequency of the harmonic for it is going to be equal to NV over 2L, where N is the harmonic number, V is the speed of the energy on the wave, or in the string I should say, and then 2 divided by the length. N can be anything from the first harmonic, or the fundamental frequency, to the second harmonic, third harmonic, and so on. To find the speed of that energy moving on that string or that wave, it's going to be the square root of the tension divided by the linear mass density. To find the linear mass density, you take the mass divided by the length. Do not confuse tension and period here. All right, next we got harmonics when we're in a pipe situation. So I have air vibrating in a pipe, whether it's open at both ends, closed at both ends, or just closed at one end and open at the other end. So if it is the same at both ends, you have 2 ends the same, you're going to use the one with the 2 involved. So that is their first one here. So the nth harmonic frequency is NV divided by 2L, where N is 1, 2, 3. V here is the speed of sound in air, because that's where our sound is vibrating. If you have a pipe that's different at 2 ends, they're odd, I have an open and a closed, we're going to be using the second one with only odd harmonics. So there is going to be a first harmonic, a third harmonic, and a fifth harmonic, and so we get NV over 4L. And again, we're using the speed of sound in air, which is 340 here. Beat frequencies, beat frequency problem because you have 2 frequencies that get close to each other. When that happens, it creates a frequency in the intensity of the sound. So it gets louder and softer, okay? And in order to find the frequency of that beat, the beat frequency is the absolute value of the difference between those 2 frequencies. And lastly, we have a Doppler effect. You know it's a Doppler effect problem because you have a moving source and or a moving listener. If that's your case, what you do is you identify your observer and your source. Your observer would be your listener, and your source would be the one emitting the sound. And you make O to S, the observer to source, your positive direction. It doesn't matter if it's left, right, up, down. That is your positive direction. You then use this equation that the frequency of the observer hears is equal to the frequency of the source times the speed of sound in air, that's going to be V, plus the velocity of the source, remember to include direction, that's why I got the arrow over it, divided by the speed of sound in air, plus the velocity of the observer, and again, remember direction there. And that is your green sheet for waves and sound.